Hi everyone, I welcome you to my channel, and today we are going to discuss the concept differential equations. And in this particular video we are going to discuss all these important points, that is what is differential equations, order and degree of a differential equations, and formation of differential equation, and solution of first order first degree differential equations, and homogeneous differential equation, and at last a linear differential equation. So in this video we are going to include all the important concepts for differential equations for class 12. First we'll discuss what is a differential equations. So for that, let me write some equations. Dy by dx plus y equal to x, say d2y dx squared plus dy by dx plus y equal to 0, d2y dx squared equal to 0, etc. So we can see that here in the first equations it involves the derivative of the dependent variable with respect to independent variable apart from the variables, okay, other variables. Similarly, here also it involves derivatives of dependent variable with respect to independent variable. So at the last here you have seen that it involves derivative of dependent variable with respect to independent variable. So we can just define differential equations that an equation is said to be differential equation if it involves derivative of dependent variable with respect to independent variable. In case in an equation it involves derivative of dependent variable with respect to only one independent variable, such equations are said to be ordinary differential equations. For example, in this equations it involves derivative of dependent variable with respect to only one independent variable. So these are all examples of ordinary differential equations. So we have equations where it involves derivative of dependent variable with respect to more than one independent variables. Okay, so these equations are said to be partial differential equations. Now, next concept that we are going to discuss today is what is order and degree of a differential equations. So to understand that, okay, let us take some examples. Okay, let us take few examples of differential equations. Now first let me define what is order of a differential equations. So order of a differential equation is the order of the highest order derivative, order of the highest order derivative involved in a differential equations. So based on that particular line, particular definitions, let us try to find out what will be the order of these differential equations. Okay. Now in this particular differential equations, that it's clearly that you are differentiating y two times. So order of these differential equations, for these differential equations, if we just write order, obviously it will be 2. So highest order derivative is 2, so order is 2. Okay. Now in this second equations, right, there are two terms involving derivatives. So here you are differentiating y 3 times, here you are differentiating y 2 times. Okay, so according to the definitions, that order of the highest order derivatives, so obviously the order of this differential equation will be, order of the differential equation will be 3, third order differential equations. Similarly, for this particular differential equation, that is differential equation this 3, so we can just write plainly what is the order. So you are differentiating y 2 times, so order will be 2. Now similarly you can write what is the order of these differential equations. You are differentiating y only once, so this is order is 1. So order of this differential equation is 2. So here if we compare these two terms, here it involves the highest order derivatives terms, so here order of this differential equation is 3. So similarly for this differential equation, the highest order is 2, so the order is 2, and here order is 1. So let us take some more examples. Okay. Now what is the order of these differential equations? Right. So order of these differential equations. Right. Order of these differential equations. It's what you are differentiating y 3 times. So order of the differential equation is 3. Okay. And next, what is the order of these differential equations? that is order, right? So in the second term, it involves d2y dx square, so order is 2. And here, what is the order? So it's first order is 1. And similarly here in the last equations, here it involves the third order. You are differentiating y 3 times, so order is 3. Okay, order is 3. Now let us try to understand. Let's see the previous examples. Okay, now with the help of this, we'll just try to understand what is degree. Okay, by degree we mean the exponent, right? The exponent of the highest order derivative term. Okay, highest order derivative term in case the differential equations is polynomial in dy by dx. First of all, the conditions to define degree in a differential equation is most important. Please try to remember that if in case you want to define a degree in a differential equation, it has to be polynomial in dy by dx. So first let us check that part one by one. Now we'll just define degree. Degree, again I can repeat, the degree in a differential equation is the exponent of the highest order derivative in a differential equations, right? And remember this exponent to be positive integral index, right? In case the positive integral index is not there, you can just simplify. You try to bring into positive integral index. Okay. Now one by one we'll try to find the degree. Now here the order of the differential equation is 2, so we need to exceed the exponent of this term. So we know that the power of this term is 1, so degree will be 1. Okay, and let us check that the second differential equations. So this particular term gives us the order of the differential equations, that is third order. Now let us check the exponent of this term. So exponent is 1, so naturally order is 1. Fine, let's come to this. Okay, this particular differential equations. Now first let us check, is it a polynomial in dy by dx, right? So have you seen this term? It is log dy by dx, so it's not a polynomial in dy by dx. So here for this 3, that is that differential equations, this third differential equations, that order, the degree is not defined. Degree is not defined. Okay, so just can write this, that degree, okay, degree is not defined. That is, degree is not defined. Now again, see the fourth differential equations. In the fourth differential equations, similarly like third, so this is also not a polynomial in dy by dx, because you have seen that dy by dx comes with an angle of sine dy by dx. So it's not a polynomial in dy by dx. So you can just write that degree not defined. So let's move to the other examples. Now from there also just try to find the degree of the differential equations. Now here in the right hand side you have seen this is 1 by 3. So just try to simplify this differential equations before you decide about the degree, right? Okay, so we'll try to raise the power by 3 both sides. Then if you raise the power by 3, this will be 3, and this 3 will cancel out. Okay, and this will be cancelled out. Okay, now this particular term gives us the order, right? So we need to check the exponent of this term. If you simplify, the exponent on the left hand side will be 3, here the exponent in the right hand side will be 1. Because we are raising both sides by 3, so that you can cancel 1 by 3. Now see the exponent of this term. The exponent of this term is 3, so definitely the degree will be 3. Now coming to this, alright, again this dy by dx terms, okay, it comes with an e to the power dy by dx. So here also for this 6 differential equations, the degree is not defined, right? Now coming to this, so it's clearly a polynomial in dy by dx, right? Because this is not dy by dx, this is only sine y. So this is a polynomial in dy by dx. So what is the degree? Let's see this term, right? Dy by dx. So order is 1. Let us check the exponent of this term. What is the exponent of this term? It's 2, right? exponent of this particular term is 2. Fine. So therefore, so we can just write that degree is, right? Degree is, okay, 2. Degree is 2. Fine. Now, okay, we can just simplify this particular expression, because we can just write this equation as, right, d2y dx square, because dy by dx one term is there, d2y dx square, okay, to the power 2. In that case, if you write, what will be the order? There will be a change in the order also. We just can write the order as 2. Okay, so the exponent of d2y dx square is 2. So degree we can just write as 2. Okay, now coming to this, that is the last differential equations. Okay, for the last differential equations, let us see what is whether it is okay, a polynomial in dy by dx. So clearly it's a polynomial in dy by dx. Now order of the differential equation is 3. So these particular terms give us the order of the differential equation. So now we need to check the exponent of this term. What is the exponent? Exponent is 1. So therefore degree is also 1. Okay. So these are the important questions that we have discussed related to degree and order. So we're just going to discuss, okay, another very important concept, that is formation of differential equation. Okay, form a differential equations representing the given family of curves, right? So here the given family of curves, that means y is equal to mx plus c. We know that this represent a family of straight lines, right? X squared equal to 4ay. This represents the family of parabolas. So from this we need to form a differential equation. So what is a simple technique to form a differential equations? Now to form a differential equations from a family of curves, we need to see that how many arbitrary constant, how many parameters are there. Okay, here we've seen that m and c, two arbitrary constant. So therefore we'll try to differentiate this particular equations and try to remove the two arbitrary constant. And you should remember one thing, that we are allowed to differentiate. That means order of the differential equation should be 2. Why? Because here order of the differential equation should be equal to the number of arbitrary constants. So here arbitrary constants are 2, so we need to differentiate twice. And with the help of that, we try to remove, that is eliminate the arbitrary constant. So let us try to solve this. Okay. So how to solve this? Y equal to mx plus c. So if you differentiate dy by dx, so this will get m, right? Because c is constant. Then, okay, we'll just differentiate once more, d2y dx squared. So this gives us 0. Fine. So what is the order of the differential equation is 2. Okay, order of the differential equation is 2. So this is the required differential equations. This is the required differential equation. Order of the differential equation is 2. And with the help of the differentiation, it is very simple questions. With the help of the differentiation, we have removed both the arbitrary constant. So these differential equations will represent the family of straight lines, that is y equal to mx plus c. And similarly, you can just solve this, the next question, that is x squared is equal to 4ay. Next question, that is x squared is equal to 4ay. X squared is equal to 4ay. So we'll differentiate this. If we differentiate, twice x equal to 4a, right? X squared will differentiate twice x, 4a, and y is dy by dx. Fine, dy by dx. So in this particular equation, which represent a family of parabolas, right? Here we have seen that there is one arbitrary constant. So the order of, so this we are differentiating once, right? So we are not allowed to differentiate more than that to remove 4a. So to remove 4a, we can take help of these equations. From this equation 1, what is the value of 4a? Twice x. So we'll just remove 4a from this equation. 4a is equal to x squared by y. So we'll replace that, x squared by y, okay, dy by dx. Fine. So if we simplify, we'll get 2xy equal to x squared dy by dx. So if you cancel x, so you'll get 2y equal to x dy by dx. So which is the required differential equation which will represent the family of parabolas. So this is a very simple technique to form a differential equations. So we have got many such questions, and I request you that you just get the concept, right? All the concept we're trying to introduce with the help of this video, okay? And after that, one by one, separate concept for one video I'm just going to upload. Okay, first we're going to learn all the concept today. Okay, next, okay, solution of first order first degree differential equations. Okay, so how to solve first order first degree differential equations, and this method that we are going to discuss is said to be a variable separable method. So the method is very simple. We don't need to remember any formula. So what we do is that we separate the variable and then we try to solve the differential equations. Okay, now the first equation we are going to discuss today is that sin x tan y dx plus sec square y tan x dy equal to 0. So if we see this question properly, then you can see that here this term containing x, here also containing x, but this term containing y. Similarly, if you see the second term, this is along with dy, this two terms sin square, sec square y and dy is there, but here tan x term is there with dy. So we are going to separate this. So how can you do that? So our concern is tan y and tan x. So we are going to divide the whole differential equation by tan y and tan x. So depending on equations, the method obviously will be different. But for this question, the simple technique is that throughout we will divide by tan x and tan y. So if we divide the first term, then by tan y and tan x, and tan y will get cancelled out, we'll get, okay, tan x. Okay, tan x. So I'll just correct this questions. This should be, right, sec square y. Sec x by tan x dx plus this is sec square y, and by tan y, right, dy equal to 0. So if you divide this one by tan x, tan y will get cancelled out. So you will get sec square x by tan x dx, right? And second term will be sec square y by tan x dy equal to 0. So we are going to integrate this, right? We'll integrate this. And we know that it's a very simple integrations. If you assume tan x equal to t, right? If we assume tan x equal to t, the differentiation of tan x will be sec square x, right? So we can assume like that, right? Say if you assume tan x equal to t, then sec square x dx will be dt. So you can just write dt by t. Similarly, if we assume tan y is t1, right? You can just write here that tan x equal to t, and you can just write tan y equal to t1. Okay, I hope you could follow these steps, right? And dt by t and plus. So we'll assume like this is t and sec square y dy will be dt1, right, equal to 0. And next, okay, we can just solve the steps here only. You can just write the answer here, fine. Now, integration of dt by t is log mod t plus, and dt1 by t1 log and t1, and we can take a constant of integrations. So you can just take the constant in terms of log. That is, you can just take the constant as log c. Okay. So we can, if we simplify, so we'll just take log a plus log b gives us log a into b is equal to log c. So therefore, t1 equal to c. t1 equal to c. Then we just replace t and t1. That is, t value is tan x into tan y equal to c. Fine. So which is the required solution of the given differential equations. Okay, you have seen that steps are really very simple. Okay, next a very important differential equation we are going to discuss, that is homogeneous differential equations. Now before we start solution of homogeneous differential equations, we need to understand what is homogeneous functions. Okay, we'll just first discuss about homogeneous functions. Let me take some examples. We'll first try to understand homogeneous functions. Let f, okay, let us consider f1 is a function of xy. Okay, that is say x squared plus y squared. Fine. And f2, okay, x squared plus twice xy. Fine. Then f3 sine xy. Then f4, okay, 10x, okay, 10x plus sec y. Okay, let us take these four different functions, right? f1 is xy, x squared plus y squared, then all this like f2, f3, f4. So what I'm going to do is, we are going to replace x and y by lambda x, lambda y. Okay, first let me make that change, then I'll discuss about the concept of homogeneous function, right? Let me write the changes here. Okay. What we'll do, that is x will replace by lambda x and y will change by lambda y. Let us see the changes on f1. So f1 is lambda x, lambda y, and the function, initial function we are assuming as, right? We have taken the function as x squared plus y squared, right? Let us, okay. Yes, x squared plus y squared. So x squared plus y squared means lambda squared x squared plus lambda squared y squared. So you can take lambda squared out. X squared plus y squared. Now in place of x squared plus y squared, it's an original function. So you can just write lambda squared f1 x y. Okay. Similarly, f2 lambda x, lambda y. Lambda is lambda y. Okay, and let us check the this function, that is x squared plus 2xy. Okay, x squared plus 2xy. Okay, x squared plus 2xy. So x squared plus 2xy means you can take lambda squared out, right? X squared plus 2xy. So in place of x, if you write lambda x, you can take lambda squared out. So it's x squared. And x will replace by lambda x, y replaced by lambda y. So you get lambda squared from the second term as well. So you can take, therefore you can take lambda squared common, right? X squared plus 2xy. So again this one you can replace by the original function, which is f2 x. Okay. Let me write the steps here down. So this is equal to lambda squared f2 x y. Fine. Right? Let's come to f3 xy, that is lambda x, lambda y, that is sine x by y. I'm just going to write sine lambda x, lambda y. So what you can do is, you can cancel lambda. So this is sine x by y. Okay, there does not exist any term consisting of lambda. You can just write lambda to the power 0. Okay, you can just express this function as this lambda to the power 0 sine x by y. But what is sine x by y? Sine x by y is f3. That is lambda to the power 0 f3 x comma y. Now most interesting is the fourth functions. Okay, that is 10x and sec y. Okay, f4 lambda x, lambda y. Okay, 10x. We'll just replace 10x, 10 lambda x. Fine. Then sec y, sec lambda y. Right? Now the problem with this particular function is that we cannot take lambda out. That means we cannot write in the form of lambda to the power n. Right? Lambda to the power n and f4 x comma y. It's not possible to write in this form because we can't take this lambda out. Okay, so this is a different function, okay, compared to all the three functions. Now what we have seen that in each and every functions, that in case the x and y you replace by lambda x and lambda y, then the function can be written in the form of lambda 2, that original functions. Okay, and here also f2, second function also you can write in the form of lambda to the power 2 into the original functions, and the third function also can be written as lambda to the power 0 f3 xy, but the fourth functions you can't take lambda out. That means you cannot take this lambda common, or either you cannot cancel lambda. That means it's not possible for the fourth functions to write in the form of lambda to the power n f4 x comma y. Okay, now so just based on that we can define this homogeneous function. So what is homogeneous function? We'll just define that. Okay, a function, okay, f xy, right, is said to be homogeneous if a function f is said to be homogeneous, if f, right, f lambda x, lambda y, right, f lambda x, lambda y can be written in the form, okay, can be written in the form of lambda to the power n, right, lambda to the power n f x comma y. Okay, f comma, for non-zero this lambda, right, for non-zero lambda, if a function f xy is said to be a homogeneous function, in case x and y if replaced by lambda x, lambda y, it is possible to write in the form of lambda to the power n f x y. The degree of this particular this function will be termed as n. Okay, that means if we can write in this way, we can say that this particular homogeneous function will have the degree n, and here lambda is a non-zero number, right? Okay, now let us move to the most important part, that is the solution of that homogeneous equation. How do you solve homogeneous equation? So that the given differential equation is homogeneous, and then solve it, right? So I'll just write this, this is dy. So show that the given differential equation is homogeneous, first part, okay? And then we have to solve this. So first part already we discussed. Anyway, I'll just discuss once again, right? But before that, we'll just write this differential equation in, right? We'll write this differential equation in standard form, okay? So what's a standard form? Okay, and this is x squared minus y squared, right? So 2xy, just simplify, and we'll just write dy by dx equal to 0. So you can simplify it clearly like that, x squared minus y squared by 2xy and dy by dx. So you can just bring this one this to the second term, that is dy by dx form, and this 2xy you can write as in the denominator of x squared minus y squared. Okay, that means this particular differential equation you can clearly simplify in the form of x squared minus y squared by 2xy plus dy by dx. And if you simplify a little bit more than that, you can just write dy by dx, and you can just transpose this particular term to that side, right? So you can, if you transpose, you can just write y squared minus x squared and by 2xy. You can just mark this is 1. So this is the standard form of the differential equations. Now let us check that whether this is homogeneous or not. Okay. I'll just rewrite the equations. This is dy by dx, y squared minus x squared, 2x, 1. Now what is the method to check whether it is homogeneous or not? Okay, just now I have discussed that we will replace x by lambda x and y by lambda y. Okay, so first of all, you need to check this particular function, right? Whether this is a homogeneous function or not, right? Whether this is a homogeneous function or not. So let f xy equal to y square minus x square and 2xy, right? 2xy. Now f lambda x lambda y, f lambda x lambda y. Now if we are replacing x by lambda x lambda y, we'll discuss about whether this is homogeneous differential equation or not, or we are going to explain also that what type of equations, what type of differential equations are said to be homogeneous differential equations. That point we have not discussed till now. We are going to discuss that, right? If we replace x by lambda x, y by lambda y, so y square will be lambda square y square. So we can take lambda square common. So it will be y square minus x square. And from lambda square, if you take common, this will be twice xy. So it will cancel out, right? So you can just write this one as lambda to the power 0. Fine. Then what is this? Y square minus x square upon 2xy. This is exactly same as fxy. So fxy. So clearly this is a homogeneous function. This function is a homogeneous function and degree of the homogeneous function is 0. Okay. Therefore, this is a homogeneous differential equations. So let me give you the definition that what equations are said to be homogeneous differential equation. A differential equation of the form dy by dx, right? Dy by dx equal to f equal to, okay, let me write this one, that an equation of the form dy by dx f x y is said to be homogeneous differential equation, right? It's said to be homogeneous differential equation if fxy is a homogeneous function of degree 0, right? You need to remember only this much. Then that particular equation is said to be homogeneous differential equation. Now quickly we are going to solve this differential equations, right? We are going to solve this differential equation. Okay, so we'll just solve this differential equation here, right? How to solve this? First, again we'll write in its standard form. Okay, first part already you have done. We have shown that this is a homogeneous differential equations. Then one implies, right? Already we have written in standard form, that is dy by dx y square minus x square, y square minus x square and 2xy. The most important substitutions in solving homogeneous differential equation is y equal to vx. Very important, please remember this. Y equal to vx. So you differentiate this. If you differentiate dy by dx, if you differentiate this, y is equal dy by dx v plus x dv by dx, right? Now, so okay, let me again mark this is 1, right? Okay. So what's the substitutions? Y equal to vx, dy by dx is equal to v plus x dv by dx. So 1 implies. So 1 implies dy by dx. In place of dy by dx, you write v plus x dv by dx, fine, equal to, so twice x, y equal to vx, fine, then y square is v square x square minus x square. Okay, we are now going to simplify this. So we are going to simplify in this way, v plus x dv by dx. So let us simplify the right hand side. Here in the denominator x square is there, and a numerator x square you can take common. So x square will get cancelled out. So we will get 2v and v square minus 1. Right? V square minus 1. Now this v we are going to transpose that side. Okay. So x dv by dx. This is v square minus 1, 2v and minus v. So we are going to use a method that we have learned in the beginning of this class today. So we are going to use the solution of first order, first degree differential equation, that is variable separable method we are going to apply here. Fine. So x dv by dx. So we'll take 2v as LCM. It is v square minus 1 minus 2v square. Okay. If we simplify this, So in case if we simplify, this is 2v, and if you take minus, since v square minus 2v square is minus v square, so if you take minus out, so 1 plus v square. Now let us separate the variables. We are going to write all the terms consisting of v along with v, dv. So therefore, this 1 plus v square by 2v will transpose to the left-hand side. So 2v by 1 plus v square dv, and this thing minus, we can just write dx by x. Fine. So we are able to separate the variable. Okay, and then we'll just try to solve. We'll integrate this. Okay, if we integrate this part, also equally very simple, the integrations, right? Why? Because 1 plus v square, if you substitute, right, 1 plus v square is t, then differentiation of 1 plus v square will be 2v dv. So you can just write this one as, so if you assume this is t and this gives you dt, right, is equal to minus dx by x. So you can just take this one as 1 plus v square, you can take as t. Fine? Okay, next. This gives us log t, right? Log more t, this equal to minus log x. And since these two terms, okay, these particular two terms gives the integrations in terms of log. So we'll just take the constant also in terms of log, that is log c. Now, log. So we'll just transpose this one. If you transpose log t plus log mod x equal to log c, right? And if we simplify, log tx equal to log c, so that gives us, okay, that gives us tx equal to c. Fine, tx equal to c, and we're just going to replace the value of t. T is 1 plus v square, right? 1 plus v square, and 1 plus v square x equal to c. Then we'll just replace the value of v, right? We'll replace the value of v, 1 plus v square, right? V square means, what is the value of v? We know v equal to, okay, y equal to vx, y equal to vx. So that gives us v equal to y by x, which is y square by x square into x equal to c. So if we simplify this, so x square plus y square by x square into x equal to c. So we'll cancel this term. So finally, what is the answer? So x square plus y square. So this x you can multiply with this dx. So which is the required solution of the given the homogeneous differential equations. Okay, the last concept that we are going to discuss today, that is linear differential equations, right? So let us discuss what is a linear differential equations. An equation in the form dy by dx plus py equal to q, right? A differential equation of the form dy by dx plus py equal to q, okay, is said to be a linear differential equations, right? If p and q are, okay, p and q are constants or, okay, constants or functions, right? P and q are functions of, right? P and q are constant or functions of x, that is the independent variable, right? So then this particular differential equation is said to be a linear differential equations, dy by dx plus py q. Remember this, these two terms are very important, p and q. These two terms can be constant or function of x. So if I just write some example, right? Say example 1, dy by dx plus y equal to x. So it's a simple linear differential equations. Why? Because what is p here? Here p, that is coefficient of y is p. P is 1, and what is q? Q is equal to x. So P is constant, Q is a function of x. Both can be constant or both can be function of x, right? So therefore this is a linear differential equation. Let me just give you some, right, more example of linear differential equations. Okay, say 1 by x, right, dy by dx. Okay, 1 by x dy by dx, xy equal to x. This is another example of linear differential equations, though it's not given in standard form. So you can definitely simplify and bring it to standard form. So what I'm going to do is, we just make this term free, that is dy by dx, we make it free. So throughout you multiply by x. So dy by dx, and if you multiply by x, dy by dx, right, dy by dx plus, if you multiply by x, so you'll be getting x squared, right, x squared y, and then x squared, fine. So what is p here? So here is p, that this term, that is coefficient of y. So here is p is x squared and q also x squared. So both are function of x, right? So this is linear differential equations. So now we have another form of linear differential equations. Okay, so we're going to discuss that also. What is the other form? So the other form is, we can just write in the form of dx by dy plus, okay, px equal to q. Exactly similar to the previous one, but instead of taking the dependent variable as y, now in this particular equation, the dependent variable is x and independent variable is y. So this is also another form. Okay, both the forms are very important. So this is said to be a linear differential equations when if p and q are functions, p and q are functions of y or constants, right? So if I just give an example, that is dx by dy, okay, dx by dy, xy equal to y. So here, what is p here? Here p is equal to x, right? P is equal to y, right? P is equal to, right? Here p is equal to y and q also equal to y. So here p and q both are function of, okay, both are functions of y, and okay, both are functions of y, and this is the second, okay, second type of linear differential equations, right? So today in our video we have discussed about, just going to discuss that, okay, what are the points that we have discussed, that is differential, what is differential equation, and we have discussed about the order and degree of differential equations. We have okay, explained about formation of differential equation. Of course, here one point we missed out, that solution of first order, first degree differential equation, that is variable separated method. I did not list it here. Okay, I did not list here. Okay, that point is missing out here. Anyway, formation of differential equation, then solution of first order, first degree differential equations. Then we have discussed about the homogeneous differential equation, and last, of course, we are just introducing the linear differential equation. And then solution part, okay, solution part will be, right, uploading video. As I said in the beginning, we are going to upload videos separately on this particular concept, that is the homogeneous, which are very, very important there, that is homogeneous differential equations, right, and linear differential equations. Okay, so thank you everyone for watching my videos, and if you are new in my channel, please do subscribe and don't forget to write a comment for the video. Okay, and please keep on watching my video, and thank you. Bye bye everyone.